So tonight's presentation is by Paul Smith, and he very nicely provided me with this introduction. So Paul recently earned a bachelor's degree in astrophysics from the University of Cincinnati and is still at UC studying for a second bachelor's in geosciences. He's also studying for a master's degree in planetary science at the University of Aberdeen in Scotland, which he's completing remotely. And he's also visiting research in the astronomy department at Ohio State University, where he studies exoplanets with the James Webb Space Telescope. And he is a brand new COC member, too.
Right. Thank you. So as you can probably tell by looking at my gray hairs, there was a lot left out of that introduction on purpose. I promise I will fill in the holes there shortly. But let me start by just explaining big picture why I'm here and what I want to talk about, and then I'll fill in those holes. So for anybody in the room who's over the age of 30, which looks to be most of us, when we were born, yeah, when we were born, there were only 8 or 9 at the time planets known in the entire universe, right? The ones in our solar system. But over the last 30 years, astronomers have discovered over 6,000 extrasolar planets or exoplanets, planets around other star systems other than our own. And 99% of them we can't even see, even with our best telescopes. So we just have to use some very clever techniques to not only detect these planets, but to learn what we've learned about them. And we've learned all kinds of things that are almost unimaginable that you can learn about something that you can't even see with your best telescope. So I'm going to share a little bit about what kind of things we know about exoplanets, and most importantly, how we know it. I don't want to just give you a list of facts, because that's only going to be so interesting. I want to talk about the clever ways that we know about exoplanets and the many things that we know about them. So that's kind of the first half. The second half, I want to take you through a little bit of my personal research that I'm doing at Ohio State. So I'll be talking about a couple of different exoplanets where I'm specifically studying the atmosphere of those planets. So that's my plan. But then back to the holes in the introduction. Let me ask 2 questions of this group. Let me see by show of hands, how many of you in the room have a degree in either astronomy or astrophysics or planetary science or something related to that? Okay. Oh, okay. All right. Now, how many of you think don't have one, but if you did, think that would be kind of cool? Okay. Okay. All right. Very good. All right. So the next 2 or 3 minutes, I want to talk specifically to those people that just raised your hands second. Okay. Because when I was a kid, maybe like many of you, I was fascinated with science in general and astronomy in particular. Right. I mean, my parents gave me my own little, backyard telescope when I was 8 years old, and I'd be out every night drawing pictures of the moon and everything. But by the time I got to be a teenager and having to choose an academic path and a career path, I made choices that I thought would be a little bit more practical to go into business. But the truth is, I just didn't have any science or astronomy role models in my life at all. Where I grew up, there wasn't a group like this. There wasn't an observatory like this. My dad was a businessman. His dad was a businessman. So I just did what I thought was expected of me. But I told myself that, someday I'm going to go back to school and I'm going to make a proper study of this stuff. But for the time being, I got a bachelor's in economics. I got a master's degree in business. I went to work for the Procter & Gamble company here in town. Spent 20 years there, had a lovely career. My last job there, I was vice president of consumer research for about a $6 billion global business unit there. I left about a dozen years ago when I decided I fancied myself a writer, and I ended up writing books. I ended up writing 5 books over the last 15 years or so, and made my living as an author and a keynote speaker, etc. But again, continue to tell myself that, someday I'll go back and make a proper study of this. And in fact, in the middle of that, I tried. In my mid-30s, I went to the University of Cincinnati. They had a night program because I had a job during the day, of course. But they had night class, and they had all the freshman courses in physics and astronomy and calculus were available at night. And I took all of them. And I just found out about 15 minutes ago that the professor that taught that first astronomy class that I took is none other than your own David Bossy over here. So it was good. Yeah, yeah. So it's good to see you again. But after I took all those freshman classes, and it took me 3 years to do it, one class at a time, because I had the day job to worry about. That was it. That's all they offered at the time at night. All the other classes were during the day, and P&G moved us, out of state again. So that was the end of that. That attempt didn't last. But, fast forward another 15 or 20 years, and COVID hit, and everybody, had a lot of time on their hands to think about what they wanted to do with their life. And I was one of those people. And I thought, you know what? It feels kind of like someday. And so I went back to UC, enrolled in the physics program, the undergraduate physics program. And I literally went back to school with a bunch of 18-year-olds as a freshman in the physics program at the age of 54. Okay. So you can imagine what that looked like in class. 4 very long years later, this happened. So I'm the old guy in the middle there. So graduating with a bunch of then 22-year-olds. Okay. So that was last year. And as she said, I stuck around. I'm studying geosciences now as well. I'm in a master's program. If things go well, a year from now, I will finish both of those programs and enter a PhD program in astronomy. And if things go very well there, in another 6 years, at the age of 66, I will finish my education after 12 more years of this and have a PhD in astronomy. I bring this up for the purpose of letting you know that if any of those people that raise their hand second think that you're just too old to do this, you're probably not. Okay, if I in my mid and late 50s can make it through E&M and quantum mechanics, there's no reason that you can't, too. So just know that it maybe is not too late if that's really is something that you want to do. That was a tough one too, but I won't make promises for them on that one. All right, so let's dive right in. So first set of topics here. So I want to talk about exoplanets in general. And what we know and how we know it. And I chose to make that illustration 2 very different exoplanets. These, if you're familiar with these, they couldn't be any more different than each other. So TRAPPIST-1e and HR-8799. And as you know, astronomers are notoriously lousy at naming things. Those are just acronyms. I think that's transiting planet and protoplanet something telescope, right? Who knows? Some of you in the room may know. HR, I think, just stands for Harvard Review or Harvard Revised Catalog of Planets. Anyway, let's dive into what we know about them and how we know it. So here's the what we know, and I'm going to spend only about 30 seconds on this, and then I want to spend most of my time on how we know it. So the one on the left is 129 light years away, very far. The one on the right, only 39, so a little closer. Right, the one on the left is almost 10 times the size of Jupiter, 10 times the radius of Jupiter, or the mass of Jupiter, and a little bit larger in radius. The one on the right is an Earth-sized planet and an Earth mass planet. So the one on the left is a gas giant. The one on the right is a small rocky planet like Earth. The one on the left orbits 16.4 astronomical units from its star, meaning 16.4 times as far from its star as the Earth is from the sun. And it takes it 49 years to make one of those orbits. The one on the right orbits at less than 0.3 astronomical units, far closer than Mercury is to our sun. So it makes it around in 6 days, 6 Earth days. So its year is only 6 Earth days long. Right, the one on the left has a slightly eccentric orbit, a little bit oval shape, not perfectly round. The one on the right is a little bit more close to being a perfect circle. The one on the left has somewhat of a random inclination, meaning the angle that its orbit is tilted relative to the Earth's line of sight. The one on the right is not random at all. It's almost exactly 90 degrees. And in fact, if it wasn't, I wouldn't even be talking to you about it because we wouldn't know about it. That's how we know about it, because it transits in front of its star as viewed from Earth, and that's the only way that we know about it. Right? The one on the left is very young relative to planetary systems. It's only about 60 million years old. The one on the right is 7.6 billion years old, far older than the Earth and the sun and all of our entire solar system. The one on the left is scorching hot. I wouldn't recommend going there, 1100 degrees Kelvin. The one on the right, 251, that's in Kelvin, which means it's almost exactly the temperature of the Earth. It would be a very nice place maybe to be if you could go there, except for the last fact, which is the one on the left has a very thick atmosphere with a very complex hydrogen, helium, carbon, oxygen, all kinds of clouds. The one on the right, we're not sure if it has an atmosphere at all. So maybe, don't book your ticket yet. We're still kind of studying that. But anyway, very different planets. And because of that, the way we learn about them are very different. So let me dive right in. To the one on the left, HR-8799. Have a look at this. And if you've not seen this before, this should blow your mind. You are literally looking at time-lapse photography of 4 planets orbiting a star that's not ours. This is the very first directly imaged multiplanetary system. It was discovered in 2008 at the Keck and Gemini telescopes in Hawaii. And you're looking at a 12-year time-lapse photography of those 4 planets orbiting the star. Okay, the star is right there in the center. We've got a little silly cartoon, 5-pointed star there because there's a coronagraph, of course, occulting the star so that the light doesn't overwhelm the light from the planets and you can actually see it. But that's where it actually is, in the middle. And you're looking at 4 planets orbiting it somewhat slowly over a 12-year period of time. But it's 120 and it's 128 light years away, and we can see it. You can see it with your eyes through a telescope or through the computer screen. Okay, and the one we're going to talk about is that one. It's labeled E. It's the 4th one found, but it's the closest orbit to the star. All right, how do we know these things about it? Well, the first one's pretty simple, parallax. And many of you in the room already know what that is, but for those of you that don't, you hold your thumb out in front of you and close one of your eyes, and then open it and close the other eye, and your thumb will look like it has kind of jumped a little bit relative to the background of whatever's behind you. That concept is how we know how far away this planetary system is. If we look at where the star system is in the sky in 1 month, and then look 6 months later when the Earth is on the other side of the sun, it's going to appear to have moved a bit in the night sky. And the reason is for the same reason that your thumb looks like it moves. It's parallax. It's close enough to move relative to the background stars. And then all you need is a little bit of trigonometry to figure out how far away it is, because we, of course, know how far we are from the sun, and we know that that's a 90-degree angle, and I'll leave the rest of it for you to figure out. It's not that difficult, right? So that's an easy one. All right, next, how far away from the star is its orbit, and how long does it take to get there? Again, this one we can see with our eyes, right? So this one's pretty easy to figure out. We literally just measure that distance, the arc distance, the angular distance, and then a little bit of trigonometry will tell you how far away it is. And as far as figuring out the time it takes, well, we just watch it for the 12 years. We can just extrapolate that and get a pretty good idea about how long it's going to take to get around. So this is pretty straightforward. The other planet that we're going to look at, you can't even see, and so we're going to have to get more creative. All right, eccentricity and inclination. So that is how circular or oval shaped is its orbit and how inclined is it versus our point of view. That one's not as straightforward. So to do that, we need very good, precise measurements of its position in space. And so what was used in this one was the Very Large Telescope Interferometer in Chile, which is just fancy language for, it's not just one telescope, it's 4. So if you put together these 4 telescopes and connect them, they behave as if they're one big giant telescope, and we can get much better resolution to figure out exactly where that planet is in that 49-year orbit. And once you've done that, you can run some computer simulations to figure out what are all the possible orbits that could fit through those data points. And there are a lot of them, but some are more likely than others. And from that, we can extrapolate that it must have this level of eccentricity, obviously not very eccentric. Most of these are fairly circular, and it must be at a certain angle relative to us. So it's based on very precise measurements, but then some computer modeling to figure out what orbits are likely to fit within those data points. All right, temperature. How do we know how hot these planets are when they're 129 light years away? Spectroscopy. We're going to talk about that a fair amount tonight. So in general, a spectra is just a fancy word for a graph that shows you how bright something is at each wavelength. So it's literally just a chart, wavelength on the horizontal axis, and wavelength just basically means the color of the planet or the star. The vertical axis, just think of it as how bright is it. So it's how bright is it at each of these different colors, because it's not always the same. That might sound unusual, but when you look at something and measure its brightness at each wavelength, it's not going to be the same. And it forms this shape here. Well, we know from experiment that hot things have a different spectral shape than cooler things. And it happens to be that a planet or a star that's about 5,000 degrees Kelvin on its surface is going to have that shape of a spectral curve. If it's not that hot, if it's only 4,000, it'll have that shape. If it's 3,000, it's a little flatter. If it's 2,000, it's a little flatter. Well, this one's a little flatter than that. and it worked out to be about 1100 degrees Kelvin. So spectroscopy helps us figure out the temperature of these things, even though they're that far away and we can't stick a thermometer in them, okay? All right, so how do we know how big it is? I told you we know the radius. Well, now we have a little bit of math, and if you're familiar with the Stefan-Boltzmann law, that's great. You know this. If you don't need to. But just know that we figured out that there is a relationship between the luminosity, L, how bright a planet is, and a few variables. And the most important ones are how big it is, and that ought to make sense. The bigger it is, it's going to put out more light, and how hot it is, the temperature, T. So if it's hotter, it's going to be brighter. If it's bigger, it's going to be brighter. And the rest of those things are just constants. They're not going to change. So we can literally, if we know how bright it is, which we can measure by looking at it, and if we know how big it is, which we just, or how hot it is, which we just figured out on the last slide, then the only thing left is radius, which we can just solve for mathematically, okay? So that's how we know that one. All right, mass is the next one. How do we know how heavy it is? Okay, now we get into a little bit more simulations, but it's not going to be that difficult. So now you're looking at a graph with all 4 of the planets, not just the one that I talked about. So we got planets A, B, C, and D around the star in the middle. What you see there are all of the potential orbits that all 4 planets could have given the observations over 12 years that we've been able to make. But if you were to make, and there's a lot, okay? But if you were to make some simplifying assumptions, it gets better. For example, if you make the assumption that they're all in the same plane of orbit, like in our solar system, most of the planets are roughly in the same plane. We're kind of like a pancake of planets. So, you know, they're not all over the place. If you make that assumption, it rules out a lot of these possibilities. And so it constrains your answers even further. And if you make the further assumption that only stable orbits that can last for millions of years are allowed and not unstable orbits, well, that removes some more of them. And now you're down to a pretty tight circle of possibilities. So now what we have is we know exactly where all 4 planets are and where the star is, and we know when they're at each location. Well, now we're just into a Newtonian math problem. So I won't share all of the math with you, but just know that, you know, we've been able to figure out, we know how orbital dynamics works now. If we know where things are relative to their star and at what time, you can calculate the masses that must be involved in order for all of those other things to be true. So we can estimate the masses. And for that planet we're talking about 10 times the mass of Jupiter is the number that worked out for that one. So now we know how massive it is. All right. Last thing, how do we know what's in its atmosphere? All right, which is the one that I'm most interested in. We're going to spend most of our time on that. So what you're looking at here are emission spectra. So their spectra, like I said before, it's nothing more complicated than how bright something is on the vertical axis and at which wavelength on the horizontal axis. But this is an emission spectrum, meaning we are directly measuring the light from the planet, because again, we can see it with our telescopes. So you see it's a little bit brighter at this wavelength and a little brighter at that wavelength and a little dimmer at this wavelength, etc. So how do we know what it's made of? I'll tell you, the first time I ever attended a lecture about spectra, and it probably wasn't one of yours, okay? But the first time I went to a lecture on spectra, because he's smarter than this, the person standing up there said, well, you know, when you look at the spectra, it's really clear that there's a water feature here, and there's clearly a methane absorption feature here, and the carbon dioxide just jumps right out at you. It's just obvious. And I'm like, are you kidding me? Well, this is a bunch of squiggles. Like, how could it mean anything? But it turns out that each molecule has a unique set of wavelengths at which it emits brighter light than other wavelengths. And each molecule has a unique set of them. So you take some of these molecules like water, methane, carbon dioxide, whatever, you take them into a lab, you put them in a Bunsen burner, you heat them up and you watch it and you measure the brightness of the light at it at each wavelength, and you will get specific spectra for each element. And if you commit those to memory, you can look at something like this and you can read it off just that simple. But to somebody like me that was uninitiated, it just looked like a bunch of squiggles. And in a few minutes, you will be able to do that too. Okay, so that has been done with this one, and those are the molecules that were found, and you'll get an opportunity to find some of those here shortly. Okay, now, if it was as simple as looking at the spectra and just picking them out, we'd be done with this part. But oftentimes, it's a lot harder than that, okay? There's 8, 10, 12, 15 different molecules in there. Some of them are overlapping other ones. Some of them aren't very strong. And it's just, the human eye is just not going to be able to pick them out. We need the help of some computers. So the main tool that I use and that astronomers use is essentially a MCMC, Markov chain, Monte Carlo. It's a simulation, like very big simulations. And I have some that literally have been running for 2 weeks now on OSU's supercomputer. So, and you'll understand that in a minute when I show you. But this is actually the spectra of a different planet, but I'm showing it to you because I found a really good illustration of the point that I want to make. So just consider this a normal spectra between 3 and 5.5 microns of wavelength. And the dots are the data. The dots are actually the data, and they've got little error bars on them. And the purple line is the model that's been drawn through it. Now, this isn't modeling that you might have done in high school or college, where you like doing a regression analysis and you've got some data and you fit a model through the line, the best fit model. That's not what's going on here. This is kind of going at it the other way. We have these giant sophisticated computer models called radiative transfer models. And if we put in all of the parameters, like all of the different molecules we think might be in the atmosphere, and we put in all the temperatures that we think the atmosphere might have at different elevations, and a number, and the radius of the planet, and the mass of it, and the gravity on it, and all these other parameters, it can calculate what the spectra should be if all those assumptions were true. So what you do is you guess, and just guess all those parameters at once, put it into the model, and it will spit out a spectra. And you hope that it fits your data, okay? And the first time you do it, it won't. Okay, and so those estimates were obviously wrong, so ignore them. But eventually you'll come across ones that work. And what I'm illustrating here is just two of those parameters: water, H2O on the horizontal, and carbon dioxide on the vertical. And if you're not familiar with these logarithm abundances, don't worry about it. Basically, to the right is more, and up is more, and down and to the left is less. So what that dot represents is one guess. So somebody guessed that there would be about 1 part in 100,000 of water in the atmosphere, a very tiny amount. And they guessed that 1 part in about 1 million, even tinier, of carbon dioxide was in the atmosphere. And then they made 18 other assumptions for all the other parameters, and they put it in, and it turned out to fit the data pretty well. So the system will keep that guess because it was obviously a good guess. But then we'll run it tens of thousands, hundreds of thousands, sometimes millions of times. And that process looks, excuse me, like this. Oop. Sorry. I wonder if when we transferred this to your computer, if the video didn't come with it. So here's what you're going to have to imagine. You're going to have to imagine a bunch of dots showing up over here, and this model jumping around like crazy as it's plotting all of them. Okay, you can probably see that in your mind's eye. What you would see at the end of the simulation is that all the dots are in a line, basically a horizontal line like this. So it turned out that combinations of low water and high carbon dioxide didn't fit at all. And combinations with a lot of water and a little bit of carbon dioxide didn't work either. But when there was an equal amount of both of them, the models fit pretty well. And the second thing that you would notice if this had worked is that the most of the answers bunched up in the top right-hand corner. Tens and tens and tens of thousands of them bunched up in the top right-hand corner. So while every one of the dots on the screen represent valid solutions, the ones in the top right-hand corner were obviously more likely. And so that's what we think is reality. Reality is the ones that show up more often than others, okay? And we run these simulations like this that, again, can take days and weeks and sometimes months. I actually talked to somebody who's had a simulation running for 5 years now. He's never going to get that published. But anyway, that's the kind of simulations that we do to answer these really tricky questions. All right, that's one planet. Let's do the other one. TRAPPIST-1, very different star, very different planet. This is a red dwarf star, less than 10% the mass of our sun. It's only 40 light years away, and it has 7 Earth-like planets around it, not just one. All right, this is one of the most famous ones. Many of you have probably heard of this before. And all of them are orbiting very close to its star. In fact, all of them are closer than Mercury is to our sun. All of them could fit within the orbit of Mercury. And they're all, here's the key point, they're all transiting. They're all at exactly 90 degrees from our perspective, so that they all transit right in front of its star, and that's the only way that we know about them. If it weren't for that, we wouldn't even know that they were there. So when a transit happens, and some of you may have seen transits of like Venus or Mercury here, you know what this looks like. So these planets and stars are so far away that we can't see them. We can't see what you're seeing here. All we can see is one pinprick of light that is that star. But what we can measure is how bright that star is. And when the planet passes in front of the star, the brightness gets ever so slightly dimmer, maybe 1% dimmer, maybe a half of 1% dimmer. But we can measure that difference. And if we see that pattern happen every 6 days, it gets 1% dimmer every 6 days, we know there must be a planet orbiting that star. And that's exactly what's happened in this case. All right. So how do we know what we know about these planets that we can't even see? Well, the first one you already know, parallax. Okay. It works the same because we're looking at the star, not the planet. But every other piece of information, we can't find out the same way as we did the other one because we can't even see these planets. So let me tell you about some of these. Well, how do you know how long it takes to get around? Well, you just figured that one out. How often does it get dim by 1%? In this case, there are 7 different planets. So this is the brightness of the planet of the star when no planets are passing in front of it. But every few days, there's a dip and another dip and another dip and another dip. And if you looked at this long enough, you'd recognize that this dip and this dip and this dip are all the same number of days apart. And the same for the ones that are in different colors here. And the ones with the arrow are the ones that we're talking about here, planet E. Every 6.1 days, it dips about half of 1%. And so that's how we know how long it takes for that planet to get around that star. All right, how do we know how big the planet is? Again, we can't even see it. How do we know how big it is? Well, we know how much dimmer the star gets. We measure that. In this case, it's exactly 1/2 of 1% dimmer. And if you know that, you can calculate how big it is because this is just junior high school math, right? Pi r squared, that's the area of a circle. Well, the star is round and the planet is round, and it must be covering up, it's covering up some percentage of the star, and you just divide those two by each other and solve the equation and you get the answer. And the answer in this case is going to be somewhere around 6 or 7% the size of the star. And if you know the size of the star, then you'll know the size of the planet, right? And we do know the size of most of these stars. All right, how do we know how far away it orbits from its star? Remember, we can't see it. Well, now this is an equation that those of you in the know will recognize Kepler's third law. If you don't, all you need to know is that there is a mathematical relationship between how far a planet orbits its star and just a few pieces of information. The mass of the star, the period of its orbit, and the gravitational constant. All of those are constants. And we know the mass of the star. We just figured that out. And the period of the planet we just learned. So we can solve for the distance. All right, so that's pretty straightforward. All right, the inclination, again, this is the easiest one on this. We know it's 90 degrees because that's why it's transiting. We can see that it's dimming the light every 6 days. So we know it's around 90 degrees, maybe 90.1 or 2, maybe 89.8 or something, but it's right in that range. All right, let me skip some of these because I want to get to atmospheric composition, and I want to spend most of the rest of my time with you on atmospheric composition. Okay, how do we know what's in the atmosphere? We can't even see it because the other one, we just looked at it. We measured the spectra and we did all the fancy, simulations with spectra. Well, we can't see this one. Okay, we have to get very clever. So when the light from a star passes through a prism in our telescopes, it makes that spectra that we just talked about that has a shape. But if there's a planet in front of it and the light goes through the atmosphere of the planet and then gets broken up, it'll make the same spectra, but there will be holes in the spectra because the atmosphere has absorbed some of it. So now we have a spectra that's from the planet and the star. We subtract the spectra from the star only, and now we have a spectra from just the planet. Pretty clever, right? And we can recognize, oh, maybe these couple of absorption, that's where water is. And maybe these absorptions represent methane or CO2 that we talked about earlier, right? So we end up with a spectra from a planet that we can't even see by that process of transiting spectroscopy. And then we analyze it the same way that I shared with you about the other planet that we can see directly. It's the same math that goes on there. All right. So what did we find about this? So TRAPPIST-1e. This is the spectra from TRAPPIST-1e. The black dots are the actual data points, and the vertical lines are the error bars around that data. The orange line down the middle is flat. Okay, that's no spectra at all, right? If it was just a big rock that crossed in front of its star, it would absorb, it would block light in every wavelength exactly the same amount, right? There's no atmosphere to absorb. So let me ask you, what do you conclude from this chart? Anyone? And do you see an atmosphere?
Yeah.
Okay. Does anybody else have a different answer?
Oh,
Say that again. Those are some, thank you, Wes. Those are some big error bars. So yes, the way a scientist would look at this and say, that orange line passes through almost all of the error bars. So the error bars is how certain are we that that data point is accurate. You know, that we're not certain it's there. It's somewhere between there and there. You know, this one is somewhere between here and here. So the way a scientist would look at this and they'd say, I can't be sure there's an atmosphere at all. If there is one, you know, maybe this, a couple of points here, maybe one over here. But the conclusion so far has been looking at this and saying, we can't even be certain that there's an atmosphere at all on this planet. Now, some of the reasons for that is that there was some stellar contamination, which means the star that this planet is orbiting had lots of sunspots and faculae and prominences, and that messes up the analysis, right? So we're hoping to get better data in the future when we have bigger and better telescopes, and maybe someday we'll know for sure whether one of these 7 planets does have an atmosphere and what it's made of. But right now, the truth is we don't really know for sure. Okay. Sorry if that's disappointing, but that's the truth. Okay. That was the first half, and we'll spend less than half in the second half, if that made sense. But I want to shift gears to my research in exoplanet atmospheres. Then we'll have a little bit of time at the end for any questions that you have. But if there's a burning one, please go ahead and ask it. So these are 2 planets that I've been studying for the last 6 months or so. VHS 1256b and TOI 2031b. Again, the acronyms are probably not that important. TOI, I think, is TESS, Object of Interest, and TESS is an acronym itself for Transiting Exoplanet Sky Survey? Survey Satellite. Thank you, Wes. Anyway, it must have been the 2031st object of interest that they discovered with that program. Anyway, and these are different. One of them is a directly imaged planet, like we just talked about, and one of them is a transiting planet that we just talked about. So VHF 1256b is 70 light years from Earth, and it is an enormous 150 astronomical units from its star. It's orbiting 150 times away from its star as Earth is from our star. And so that's it. This is the star. That is the planet. And this is an actual image taken with the James Webb. It turns out it's about 14 times as massive as Jupiter. So it's very big, but it's very young. It's only 140 million years old, and it's very hot. But why is it hot? If it's so far away from its star, why is it hot? It's not still accreting, but you're getting close. Yeah, it's young, and so it's it's huge. It's very massive. In fact, if it was any more massive, we'd call it a brown dwarf. And basically it's an almost a star, right? So it's got its own internal heat that, you know, a couple of billion years from now, it's not going to be hot anymore. But right now it is, because it's so young and it's so massive and it's generating its own internal heat. Okay, so this is actually the James Webb Space Telescope near infrared spectrograph that myself and other people use to get spectra from these stars. Now, so this is not the one that I worked on, but it was used on July 5th, 2022 to observe that planet. And so what we're going to look at now is what we learned from that. So this is the spectra from that observation, right? The colors just are from different instruments on James Webb that took it. But notice it's just a spectra. It's brightness over wavelength. So what I'm going to do as an experiment with this group is I'm going to show you, in fact, I'll show you now. These are opacities of various different molecules that are often found in planets, in gas giants. So again, all this means is, it says cross-section, but just think of this as brightness on the vertical axis, and again, wavelength on the horizontal. So, and you've got the different colors represent, you know, water and ammonia and methane, etc. So what these shapes represent is at some certain arbitrary temperature, so this one is water, at this particular wavelength is going to be brighter than at this wavelength. And it works the same in absorption as well. It will absorb more at this wavelength than it does at this wavelength. So since we're doing transit spectroscopy, we're looking at absorption of the light from the star through the planet's atmosphere. So what I'm going to do, I'm going to take this graph and I'm going to turn it upside down because it's absorption, not emission that we're going to do. And I'm going to spread it out so that it matches this spectra. And I'm going to put one on top of the other. And then I'm going to ask you to see if you can find what the atmosphere is made of. Okay. Now, I'd like to give the first 3 guesses to only the people who raised their hands second earlier this evening. All right. The people who don't have science degrees, but think that it'd be pretty cool if you did. And then after 3, I'll open it up to everybody. And I actually have some prizes for correct answers. So these are lunar brass coins, I guess. They've got all the, this has nothing to do with Artemis. I bought these a long time ago, but it's kind of nice timing. So it's got all the near side craters on one side and all the far side craters on the other side. So I've got enough for a few people. All right. So are you ready? Do you understand the challenge? Right? All right. So raise your hand when you see. Oh, sorry. Yeah. So ignore the colors. Just look vertically. What shapes up here do you see directly below? Okay, who said that? Did you raise your hand second earlier, or are you one of the scientists? Okay, all right, you do. Okay, all right. I don't want any astrophysicists jumping in here and stealing. All right, this one's for you. All right, so what she found was water, the blue one. So it's the most prominent one. You see all of these dips right there. They match up with these dips right here. Okay, and it's not, and again, ignore the color. This dip right here is this dip right here. All right, next. Who's next? Who sees something? Right. Carbon monoxide. Very good. The purple one? Yeah? Okay. I love this one just because the shape to me looks like a W or maybe a mustache. Right? Yeah. So what she's looking at is this W shape here is this W shape right here. So Julia, congratulations. Well done. All right. Who's next? Yes, Chuck. Methane. All right. He's looking at this one right here, the purple one. You see that little dip right there? That is that dip right there. Well done, sir. All right. Now it's open to anybody. Any others that use that? There's probably only 1 or 2 left that can be seen by eye, but I'll take it. Yes. Yeah, well done. Okay, so potassium over here is the K. If you look, I think that color is this color here. So were you looking at something down here? Yeah, I agree. I think that dip is probably that dip there, and this dip maybe there's that one. Well done, sir. Can you pass that back, Tim? Anybody else see something? I'll give you a hint. Yes. I don't see that one. Which of these places are you thinking here? Right, this one and this one. Yeah, I thought about that too because this one matches here, but I think that's really water because this dip is a bump here. So I think it's not. I'll give you yes in the back. Well, yeah, we did that one. That's methane. Yeah, but you're right. If you're looking at that, that's methane. I'll give you a hint. I think it's close to the potassium one. Yeah, who said that? You don't count. Okay. All right. I'll leave a couple up here for the first people up after. But yeah, I think it is this color. It's the Na, sodium. I think that's this one right here. So it's close to the potassium one. The rest of them, I think you just can't see by eye, and that's why we use those fancy simulations that take weeks and weeks to run. But you've just discovered a molecule on a planet dozens of light years away. So congratulations. How about a round of applause for all of you? All right, last one. The other planet, TOI 2031b. So this is one that I'm currently studying. I'm part of a team that just won James Webb Cycle 4 time last September. The reason why you see this, don't take pictures. They made me put this on here. The data I'm about to show you has not been released to the public. You are going to be among the first people to see this. There have only been about 35 or 40 people on the planet Earth who have seen this data, and it's going to be about 100 now after tonight, okay? But I just ask that you not take pictures. So I'm on a team here with all of these people studying this planet's atmosphere in particular, and the question that we're studying essentially is, how did this giant planet get so close to its star? Because I probably should have started with this, a little bit about that. So this is the star, but you can't see the planet. Again, it's way too far away. We only know it because it's transiting. But we know that it's a warm Jupiter, meaning it's a gas giant planet, and it's fairly hot, but not super hot. So we don't call it hot, we just call it warm. It's 900 light years away from us, which is why we can't see the planet. It's bigger than Jupiter, and it's a little bit less massive, but it's very warm. But it's orbiting super close to its star. So its year is only 5.7 days. It makes a complete orbit around its star in 5.7 days, and its transit time is only about 4 hours. So every 5.7 days, for 4 hours, the light from this star gets ever so slightly dimmer, and that's what we've been looking at and measuring. And so we got, on September the 18th of last year, we had 8 hours of James Webb time all to ourselves, and this is what we pointed it at. And I'm going to show you what we found. But before that, I want to tell you what we expected to see. Right? So what we expected to see was one of those transits where the light, it's called a light curve, where it dips for about 1% for 4 hours and then goes back. But if instead what we got was just a flat line, what would that tell you? What's that? Well, it could mean that there's no atmosphere, but we know it's a gas giant, so we know it has one. So what's the only other reason why the line would be flat? What's that? No. Yeah, it's transparent. No. The reason is more obvious. You're thinking way too hard about this. Exactly. It would have meant we missed it. We pointed the telescope at the right star at the wrong time. Okay, so the first thing you do when you're an astronomer and you get data from the James Webb Space Telescope, when you're doing transit spectroscopy, the first thing you do, it's called first look. You look to see if you got the transit. Before you do any of the fancy math, you just need to know, did we point it at the right place at the right time? And out of all those 33 scientists, I happen to be assigned the job of first look at this planet. So my poor wife I kept her awake on September the 19th at 4 o'clock in the morning as I'm waiting for this data to come in, and I'm so excited for it to come in. I want to see if we got it. And when I get the data, it's not like a picture shows up on my computer. All I get are a bunch of zeros and ones, and it takes me hours of data processing to get the chart. But I finally got the chart, and give me a drum roll on your knees, please, and I'll show you there we go. Yeah, we got it. Okay, so I was very happy. But what looks weird about that? Yeah, what's that? I didn't order that. Is there a bug in my telescope? Yeah, so I was very happy to see a light curve. So we got almost in the middle, about 2.5 hours of before the transit, 4 hours of transit, an hour and a half after the transit. But that little bugger there bothered me. What do you think could have caused that? Yes, in the back. Okay, I thought about that. Could there be a moon? But that turns out not to be it. That's an interesting guess, though, but that's not it. Was there another guess? Yes. Yeah, that turns out to be the case. That's what it was. It was a cosmic ray. So what that means is a highly charged particle like a proton by itself or an electron by itself. Sometimes I guess there are the helium nuclei, alpha particles. But anyway, these things are flying all around the universe, and if they slam into your telescope when you're using it, it can cause a problem. So what I had to do, so I knew when the problem happened, because this is a timeline, right? The problem happened, and by the way, it's taking exposures about every 90 seconds, right? There's 376 exposures that we got over 8 hours, right? Exposure number 296 had a problem. So I knew when to look, but I had to find the place on the detector And it's a big detector, and I had to look all over it, and there's lots of different files to look through, but I found it. And it was this. And that cosmic ray that you're talking about is right there. That white line is literally the light being spread out across the detector horizontally. And if you zoom in on that, all these little red dots are places where the pixel is bad for some reason. Either got overheated or the pixel is just burned out and you can't fix it. It's out there in space, or something else. But you shouldn't have a big blotch like that, if things are going normal. That is a cosmic ray hit and messed up that part of the observation. So once I knew what it is, I can account for it and get it out. But anyway, it was a nice little scavenger hunt to figure out what was wrong with it. So once I fixed it, it looked like this. And what I want to point out here is, we used all those error bars later. Any good scientist uses error bars. There are error bars here. You just can't see them, because the James Webb Space Telescope is so freaking awesome that its reliability is just amazing. And so there are error bars on there, but they're just very, very, very tiny. If you use a ground-based telescope, transit light curves often look more like this, So you can definitely see there's a dip there, but it's certainly not as clean as mine. And the worse they get and the worse they get, you can have ground-based telescopes that's your transit data. And if I didn't put a red line through that, you might not even know there was a transit, right? So I feel very fortunate getting to use a telescope that can deliver this kind of resolution. So how do you build a light curve? How do you build a spectra from this data? You literally look at a light curve and measure the light curve at every single wavelength. And the James Webb can split up into 3,900 and some odd wavelengths for this particular spectrograph that I'm using. So you do that 3,900 times, once for each wavelength, and you measure the amount of dip that is in it. Notice this dip is different than this dip, and then you put them all together and you get a spectrum. Now, it's a little more complicated than that. I've got to account for a lot of other things like the eccentricity and period of the orbit and limb darkening and other effects. And I use all of that same sophisticated modeling that I showed you earlier. But at its core, what it's doing is this. It's plotting out a light curve for each different wavelength and then plotting what's left. And here's what it looks like. So once I had finished all of that work, the day after we got back from vacation, what I got was this. So let me explain a couple of things. First of all, that gap in the middle, that's not a mistake. The James Webb has two different detectors. Each detector is like a big CCD chip like is in your phone. It has two of them, and there's a gap between them. So that's all that is. There's just a gap between the detectors. But as it looks now, you can't see any spectra in that. You can't see anything, right? It looks useless. So what you do is you take the first, say, 5 data points and you average them together. It's called binning. You bin them together. And then you take the next 5 data points and you average them together. You do that all the way across and you get something. Oh, sorry. You got to put your error bars on it. And so now you really can't tell what's going on. But then you start binning. So now I've got it into 200 bins. Well, now that you can maybe start to see a little shape appear. What if I bend it a little further? Now it's 100. Well, now something's starting to appear. What I ended up with was this. Okay. So now it's got a shape that we can do some analysis on, okay? And we did. Now we're still doing this, and again, this is the data that's not been released yet, and we're not even done doing our analysis, so we might come up with something different. But so far, what we see is water. So this is only, by the way, 3 to 5 microns. So you were looking earlier at really big sets of spectrum. This is a very narrower area. But this is that water curve that one of you identified earlier. Which it's up here, and this is what it looks like. Over here, I think you found carbon monoxide. I think this one is carbon dioxide. Yeah, I think that one is carbon dioxide. So that bump right there is carbon dioxide. Now there are others that the simulation tells us are in there that are just hard to see by eye, and we'll have to run a bunch of tests to verify that. But this is kind of what we've figured out so far. So it's got a lot of hydrogen and a lot of helium, and some water, and some carbon dioxide, and methane, and a few other things, and that's it that we can tell so far. So what that tells us, oh, and by the way, we can actually also tell how much of those there are at different altitudes within the planet, which is really, really interesting, all right? Again, a planet that we can't even see, we can tell what's in its atmosphere, and at what altitude, and at what temperature, and at what pressure level. So what that tells us in general is that this planet has a high level of what astronomers call metallicity, meaning it's got some hydrogen and helium, or it's got a lot of it, to be fair, but it's got more of all the other elements than our sun does. In fact, about 10 times as much. And it's even got more, it's got a higher carbon to oxygen ratio than our sun does. What that tells us, that helps inform us on the main question we had going in, which is, how did this, I should have articulated it better to begin with. How is it that we have this big giant, gas giant planet that should be way out away from its star? How come it is so close? How did it get there? And there are a couple of different theories about how they get there. One is first they form way out beyond what's called the snow line, way out where it's cold enough for all these chemicals to condense and accrete together and begin to form a planet. And what will happen is they will end up spiraling in towards the inner solar system while the planets are all still forming and there's still a planetary disk. And that's called disk-driven migration. That's one option, one theory. The other theory is, no, it formed out there and it stayed out there and it would have been happy to stay there, except some rogue star came flying by or some other big object, and it just gravitationally flung it out of its orbit. And so it kind of, it got perturbed and then ended up into a highly elliptical orbit, sometimes coming very close to the star, sometimes being very far away from the star. And when that happens, there are tidal forces and frictions that will end up bringing it all in closer to the star. But when it does that, it's not spiraling around in the planetary disk where it's scooping up a lot of dust and pebbles and other things that increase its metallicity. So because we determined that this planet has a high level of metallicity, a lot of those non-hydrogen and helium gas elements, we suspect that it followed this path, not this path, to get to where it is. So it formed way out in its system and migrated in, but it did so in this kind of a method. That's our hypothesis right now, and we're going to study 4 other planets like this and see if we can draw some conclusions from them. So that's it. Let me stop there and ask for questions. Thank you. Yes.
What elements or chemicals or molecules were at what elevation within the atmosphere? It's driven the pressure information you got from the spectrum that says it's higher level. You got the pressure for the entire atmosphere?
Yeah, so 2 things to answer that question. Yeah, it's not, we're not really looking at the altitude, we're looking at pressure, but you can infer pressure goes along with altitude. We use chemical equilibrium models. So for any of the chemists in the room, there's thermochemical equilibrium for certain, you probably know this better than anybody here. There are certain chemicals that, chemical reactions that are more favorable at certain temperatures and pressures than others. And so that's why, yeah, we know that some of these chemicals, once they get up to a low enough pressure, will disambiguate. That's probably not even the right word, but they will no longer be bound. And some of these reactions will only happen at high temperatures. And so we have that all built into the model. So once we measure the total amount of it, we can then plot where it must be in the pressure temperature profile of the planet. Yeah. Yes. So in the back and then up here. How much long? What? Oh, this one is lower mass than Jupiter, about 20% lower mass, but it's about 25% larger in radius, so it's less dense. And there are some that we call super puffs. They're like really, really puffy and low density. This is not one of them, but it's slightly larger than Jupiter, but slightly less massive. So, and when people say failed stars, they're normally referring to brown dwarfs. This one is not nearly big enough to be a brown dwarf. That's normally, Wes, correct me if I'm wrong, in the 12 to 14 Jupiter mass range that we consider it to be a brown dwarf. Did I get that right? Somewhere in that range. Yeah, but something that's only around 1 mass of Jupiter is nowhere near massive enough. It needs to be somewhere in the 12, 13, 14 mass of Jupiter before it can start to, it's not going to burn hydrogen at that point. That's like 80 Jupiter masses before you have real stellar thermonuclear burning, and it's a real star. But these brown dwarfs are kind of halfway between planets and stars. And so this one is nowhere near that. This is definitely a planet-sized object. So, question up here?
What caused it?
Yeah, a great question. So the gas that's in the planetary disk, as everything is forming, the gas surprisingly doesn't follow Keplerian orbits. Like it doesn't follow the orbit that you would expect it to if it was just a rock out there by itself. And I think it's because you've got pressure from the stellar winds that they can kind of blow the gas out. So it's got not just gravitational forces acting on it, it has this pressure pushing it out. Whereas the planets and rocks and planetesimals and things like that are kind of unaffected by that stellar wind. So you've got this gas that's not really moving the way it should, and there ends up being a little bit of a drag on it. There's more sophisticated reasons than that. I think the gas that's further out tends to pull it one way and the gas inner pulls it another way, but the net effect of all that is that it ends up slowing down. And if it slows down, it's going to spiral in. If it speeds up, it's going to spin out and go away. And it turns out that they spiral in. Yeah. Yes.
If it's that close to its sun and it's very gassy, will it eventually evaporate?
Yeah, it could. Because yes, it definitely could.
Go back out.
Yeah, because there's a lot of stellar wind at that level. But these are also pretty massive stars. So there's a lot of gravity on them. So I'm not even sure I know the answer to that. Do you know what the future of close-in gas giants are? Okay, I don't know. I'm going to probably look that up and try and get you a better answer for that.
Okay.
Is there two more? Yeah.
Yes, so real quick. What could have really?
Yes, and they do. So for a gas giant, tidal forces are less damaging because it's just a ball of gas anyway. But when you have rocky planets, or when you have moons that are orbiting very close to their planets, the tidal forces wreak havoc with them. And so they create a lot of internal volcanism and things like that. So, I mean, we have planets in our solar system, Io around Jupiter and others that are very volcanically active, specifically because of the tidal forces that are on it because they're so close to their planet. But it just doesn't disrupt a planet this much. It could get close enough, though. There is a distance, the Roche limit. So if it gets closer than the Roche limit, then it's just going to tear it apart, and it's going to get sucked into the star, right? But these are outside their Roche limit, at least for now. But they very much could continue to spiral in and end up below the Roche limit. Yeah. Yes, sir. Okay. Okay.
What would the sales pitch be?
Yeah. You know, I think the best answer to that question I've ever heard was, you know, studying things like this. It's not curing cancer. You know, so there is less direct human benefit from doing astronomy and astrophysics. There are always the ancillary benefits of, you know, when we do a lot of space work, it ends up helping out our military. They always end up using our technology somehow. But I think the better answer is, you know, while this type of work won't cure cancer and it won't, you know, help you defend this country, but it will make this country more worthy of being defended because we will just know more. We add more to, I don't know, society's knowledge, and people want to know this stuff. I mean, if we found out that there's life on a planet, you know, 1,000 light years away, nobody's ever going to go there, right? So it's not good, you know, there's no planet B, right? So, I mean, there's planet little b, but there's no big B. Like, we don't have a backup plan, right? That anywhere in the next 1,000, 10,000 years, we're not going to end up on some other planet with everybody living there comfortably outside of our solar system, that is. So finding life somewhere, the only reason we want to do it is just because it's interesting, right? So I think that's the answer. Anyway, you let me know when we're done. I think we're probably beyond our time, so you tell us what to do. Yeah. Yeah. Yeah, well, all on Zoom because we're all over the world. So I mean, there are people on this team in Europe, all across the country. So yeah, we have a Zoom meeting once a week, just like everybody else does in the world today. But the way we get together is, I mean, the PI, the primary investigator on these projects, they pick the team that they want, and they can pick people anywhere because we can all meet this way now. I mean, you know, we don't have to go to an observatory to get our data. We just log on to the, you know, MAST system, the NASA archive, and download our data when it's ready. So we can do it from anywhere in the world. Yeah.
You're talking about why we do this, but as we do this, we learn new laws of physics. In 1900, no radar,
Right.
no radio.
Yeah.
By studying things, we figure things out. Einstein said there can be Einstein and Rosenberg.
Right.
Well, before that, he had no clue.
Nobody knew.
We can't do it yet, but maybe someday.
Right. Now, there's a better answer to your question right there. Yes, sir. So it's very common that the planets are in a plane. It's not very common that they're in a plane at 90 degrees to us. So just the hydrodynamics of a ball of gas that is contracting, and therefore angular momentum is going to make it spin faster and faster and faster. It's going to flatten out into a pancake for the same reason as when the guy tosses your pizza up in the air and spins it, it flattens out more and more and more. That's just physics. So it's very common, and the planets form out of the gas and dust in that planetary system. So it's very common for them to all be in a plane, but the orientation of it, only 1 or 2% are going to be aligned with us. So there are probably, or we know there are many, many more planets out there that we'll never be able to see this way because they're just not oriented the right way. Yeah. Yes.
Short big defense science.
Mm.
Then we look it up.
Yeah.
He's to the point, but it's Sanskrit.
Yeah. Oh, good. I haven't seen that. I'll check that out. Thank you. Yes. Yes. Is there anything different looking in the infrared than the visual? Yeah. So you're looking at different wavelengths. So different molecules have different features in different parts of the electromagnetic spectrum. The reason the James Webb was built to look in the infrared, we already had Hubble, and Hubble's is the visible wavelength range most of it. I think does it have a little bit of a UV on it? Okay, and a little bit of IR. But James Webb went even further into the infrared. They built James Webb that way so that they could look at galaxies far, far away that are moving away from us so fast that they've been redshifted. So all of their emission spectra would be in the infrared now instead of the optical. But it turned out it was good for looking for planets like these because a lot of these molecules have significant recognizable absorption features in the infrared that are harder to detect in the visible. Yeah, so it works for us in exoplanet research as well. Yeah. Anything else? Yes.
It starts.
Okay. Yeah. So ask, now I know you're talking about not the sun, but yeah. So ask the question again. Yeah. So in these, we're not using a coronagraph to block the star.
Stuff coming from the surface or the stuff coming from
the the corona, you're talking about this. Yeah. So, it does vary a little bit, but it's really crossing the photosphere that you see the main drop. So the corona is so light and whimsy that it's not going to affect the light very much. But what that does remind me of is, I mentioned the word limb darkening earlier. As you look at the sun, and you guys have probably, many of you done solar astronomy, when you look at it, you notice that it's brighter in the center and it's darker near the edge. So we have to take that into account too. It is dimmer as you get near the edge of the sun. So as the planet is transiting, that light curve, that's why it's round at the bottom instead of just jutting across and going back. It's because it is dimmer at the limbs. That's called limb darkening. Thought I saw one more. You? Yeah.
You said the direct observation was the one closer. You know the limit of how far, like the direct observation has.
Oh, my guess is it's somewhere in the 100 to 200 light year range. Beyond that, it would be really hard to do, but I don't have an exact number for you, but it's in that range somewhere. Like the second one we're looking at here is 900 light years away. It's transit. There's no way we would see it. But, one of those I think was 129. It was a directly image. So somewhere in that range is, but once you get beyond maybe 200, I think we'd need a bigger telescope. Yeah. Yes. Yeah. Thank you. All right. I'll stick around if you have any other questions, but thank you very much for your attention.